the chance to talk here and meet with everyone here and have many interesting discussions too. So what I'm going to talk about today is the quantum logic control of a single molecular ion. And I should point out first that this is by far not my work alone. There are a lot of people involved, and I want to particularly emphasize that nothing of this would have happened without James Job, who came back to NIST and then really made it his mission to get this experiment to work. And there's Didi Leibfried, another NIST staff, and postdoc Alejandra Colapi, Dalton Chaffee is a grad student, and then we have last postdocs, Yi-Heng Lin and the postdoc Christoph Kurtz, who also had many contributions to this experiment. So let me start, and since I'm the first person talking about molecular ions, there's one thing I should maybe mention. Probably you know the famous quote by Schrödinger that we never experiment with just one electron or atom or small molecule. And we've already done a lot of experiments with atoms and electrons, but now we even have an experiment where an atom and a small molecule work together in one experiment. And another thing that Schrödinger abhorred, quantum jumps, will play a prominent role in how we can actually find the state of these molecules. In any case, quick introduction to molecules. In atoms we have electronic transitions and we have fine structure and hyperfine structure couplings. In molecules we have a lot more degrees of freedom. There's the vibration. This doesn't really work the way it should. This should actually, anyway, there's also the vibration in the trap. So there's the vibration, there is rotational degrees of freedom, and then these nuclei can have spins. There is also, if the charge and the center of mass are not in the same place, the center of charge and the center of mass, you can have a charge that goes around the center of mass, which creates a magnetic moment. That's called the rotational magnetic moment. And so all these degrees of freedom can interact with each other. You have a lot more couplings. And what's important for this talk, we are in a room temperature environment, and typically the electronic degree of freedom is in the ground state because the typical temperatures are much higher than room temperature, and even the vibration is in the ground state because that's about, for very loose rotational vibrational transitions, that's on the order of room temperature. So it's particularly in the hydride molecules that I'm talking about, you're basically always in the vibrational ground state if you're equilibrated with your environment. The rotational transitions are a different story. That's typically smaller than room temperature, so you will be in a distribution of rotational transitions. And then these smaller spin and rotational couplings, they're all way below 1 Kelvin, so typically you'll be in a big distribution of those degrees of freedom. Alright, so that's basically where we start with our molecules. We would like to treat molecules like atoms. We would like to laser cool them and do the same kind of spectroscopy that we love and know with atoms, but unfortunately they work differently. So when you typically absorb a photon in a molecule and you're in an excited electronic state, there is no close transition unless you're in very special molecules that allow for that. But there are not many of them, they are very special. If you think about it, even in atoms, these close transitions are kind of special. We can't just laser cool any atom. We have to take special ones that work for that. And in molecules, there are a lot more of them, and having these special cases are even rarer compared to the number. And so typically when you absorb a photon in a molecule, you can end up in a lot of vibrational states in the ground state upon emission. And so that is a problem, because if I scatter a photon here, I'm basically lost in Hilbert space. There are ways out. I already mentioned one. You can take these special molecules where you are actually bound to emit to more or less the same state. That's called the diagonal Frank-Condon factor. But that restricts your choice of the molecules quite a bit. Another way you can do it is you can actually control the state of the molecule by building it from well-controlled atoms. And there is quite an industry doing that, where you take ultra-cold atoms, you put them together, and you have your molecule potentially in a good state. There are other tricks, and I think Brian will tell us a little bit about that, how you can get into the right state of the molecule. But what you want to avoid in any case is spontaneous emission of the molecule, because that basically makes you be lost in low-bit space. So if you avoid spontaneous emission, you won't get any light from the molecule. And that means you don't really have anything to observe typically. So that's the problem. And the trick to get around it is we can use motion as the messenger, at least if our molecule is an ion. Because then we can use what's called quantum logic spectroscopy. And the trick here is we put another atomic ion next to the molecule. And then, for example, we cannot only excite this molecule to some state 2 here, that should also be metastable and maybe not electronically excited. I'll explain in a moment how that works. But we can actually do this on a motional sideband. That means we put a little extra energy in here. So other than exciting to this other state in the molecule, we also make this guy oscillate a little bit from the recoil of this photon. So it's oscillating a little bit, and that means that our atomic ion that we can control very well and we can read out and so on, that will also jiggle a little bit, and we can then detect this on the transition of this logic ion, where basically we can use a little bit less energy because we have this extra energy in the motion to excite it to an excited state that maybe gives us a photon. So that's speaking very roughly how this works. And of course, this is very general. It's not just working for molecules. You can think of all kinds of things. This is how the aluminum frequency standard works at NIST and also in other places by now. You could also think about controlling other things like electrons, antiprotons, or whatever charge system, because as long as it has a charge, it can oscillate in the potential of the trap, and it can couple it to your logic ion. So that's the basic idea. How does the quantum logic spectroscopy work? Basically, if you have 2 ions, you can think about normal modes of these ions, and you take one of these normal modes. If there are 6 in total, but you can ignore 5 of them, and you can take one of them and cool it to the ground state. So that's the initial situation we have here. We have, for example, a molecular ion. It could be something else too. But the molecular ion, and we share a motional ground state between the molecular ion and the logic ion. Now I can try to excite this molecular ion, and I do this not just exciting the internal degree of freedom of the molecular ion, I also try to do this on a blue sideband. So I go from n equals 0 to n equals 1. And the decisive thing here is that when I do this, when this transition happens, because this is a shared degree of freedom, the logic ion, the normal mode of these 2 together, is in n equals 1. So it's shared, and they both make this transition. And that now means that when I excite the red sideband here, the logic ion can make this transition. This has to be compared to this other situation where when the molecular ion is actually not excited, you excited it with the wrong frequency, you don't hit it at just the right frequency here, then here you make the transition, here you don't make the transition, you're still in n equals 0. And therefore, if I now try to excite the red sideband, I don't have enough energy to do this. And when you compare the final states, in one case, you're up here, and if I try to now drive the cycling transition, I will get no photons, while here I'm still in this ground state, and I can see photons. So depending on whether the molecular ion has made a transition or not made a transition, I will see light from the logic ion. And there is an additional benefit here. When I see the signal from the logic ion, I'm not really doing anything to the molecular ion. So other than in a typical experiment with ions where you basically destroy the state that you're in because you're going to the p state, the molecular ion state is still there. So you get a signal that you've made a transition, and that tells you that you must be in the final state of that transition. And even if you have made a pi-half pulse or something like that, so you might be in a superposition, at the moment you detect here, the system has to decide which state it's in. And so you're either here or here. And that means that this molecular ion is now in a pure state because you know exactly where it is. Another way of saying the same thing is you have the information where the molecule is. Alright, so this is just in shorter words what I just said. And now, of course, that's only one part of it. I still can't excite to electronic states, but there are simulated Raman transitions that we used for a long time in atoms to do our bidding for quantum information. You can also have simulated Raman transitions in molecules. That's slightly different than what typically molecular spectroscopists talk about. They put one photon in and then the other one is spontaneously emitted. In the stimulated case, you have two sources of light, laser 1 and laser 2, and they are different frequencies, and you basically are very far detuned, or we typically are very far detuned from the excited electronic state, so populating anything up here is very unlikely. But by the energy difference of these two photons, we can make resonant transitions between, for example, rotational states in the ground state, or it could also be vibrational states. That would mean that this energy difference has to be quite a bit larger. So it could be anything in the ground state, for example, that you bridge in this way, and all you have to fulfill is that the laser frequencies have to correspond to the initial and final energies here. So how is the experiment really done? We basically trap a logic ion and a molecule in a trap. In the axial direction of the trap, we get two frequencies of motion, omega plus minus. It depends on the relative mass of these two ions, what omega plus minus are. And that's basically done by the Coulomb interaction. And one thing to remember here that's important is that this is a frequency, it's a harmonic oscillator, but this is the external motion of these guys. It has nothing to do with the vibration of the molecules. So the harmonic oscillator I'm talking about here with omega plus minus is the motion of these guys. And the nice thing about ions is that the Coulomb interaction makes them talk to each other all the time. So I can laser cool this logic ion, and by association I will cool the external motion, the translational motion of this molecule. However, the vibration and rotation of this molecule is very weakly coupled to this ion. So as far as vibration and rotation goes, it's almost like this guy is not even there, because it's a few microns away, and all the interactions here are rather weak. So basically you can think of the molecule as being held in place, and also I can read it out, but at the same time the internal degrees of freedom are more or less free to do whatever they want. They don't really know that the logic ion is here. But I can cool this to the ground state and then use the motional state of this 2-ion crystal as the messenger. A quick word about the normal modes. We use in our experiment calcium and calcium hydride, so the mass difference is very small, and that means that the normal modes look almost like you had two identical ions. So the center of mass mode, in quotes here, is nearly equal, has nearly equal amplitude, and is very close to what the single particle oscillation frequency in that potential would be. And then the stretch mode is pretty close to square root of 3 of that single particle oscillation frequency, but that's just because the masses are very close. If the masses are different, this works out a little differently, but we can still speak of an in-phase mode where the ions move together but with different amplitudes, and an out-of-phase mode where they move apart. And so this works universally, almost universally. The masses can't be too different, but they can be different, and the whole thing would still work more or less. So as I already mentioned, we use calcium hydride, and so it has molecular energy levels. You can read about that in various papers. But this is basically what it looks like, and we are concentrating on this 1 sigma ground state here. So blowing that up a little bit, there will be vibrational states in this ground state electronic potential, and then blowing it up again, you have the rotational states. The distance between rotational states between 1 and 2, for example, is about 0.6 terahertz. So this is a fairly large frequency, but not optical frequency. And it's actually pretty hard to get sources that would work directly here. But we'll use Raman transitions to look at that later on. So now concentrating on these rotational sublevels from the angular momentum, you probably remember there are M states like this for 1, 2, 3. We also have the proton spin here. So because of the proton nuclear spin, each of these levels is actually doubled here. And as I mentioned in the beginning, all these energies here are relatively small or on the order of room temperature. So when you start with your molecule, you don't really know where it is. It can be in any of these states, actually up to 11, so somewhere up here. And basically, there's a very small population in each of these sublevels at room temperature. It's smaller than 1%. And that's a problem. You now have to find where the molecule is, or you have to somehow get it into a place where you can find it. Concentrating again on just the J equals 1 here. We are in a finite magnetic field because we would like to know what the quantization axis of our calcium is. And interestingly, there is something that looks a lot like the hyperfine Hamiltonians that we are used from atoms, but this is actually when the rotation of the molecule couples to the nuclear spin of the hydrogen. So again, you can think of this as calcium has already 1 electron less than it would have in the neutral state, but nevertheless, because it would like to be noble, and there's 1 valence electron, it would like to share the electron with the hydrogen, which would like to acquire an electron because it would like to look like helium. And so basically, one of these electrons, the electron that the valence electron is cheating over a little bit to the hydrogen. That's one way you can think of it. And that means that the center of mass, which is almost exactly in the calcium, it's 40/41, so almost in the calcium, will not be the center of charge. That will be a little closer to the hydrogen. And so you have basically a charge distribution going around the center of mass, and that gives you a magnetic moment. That's this rotational moment. That's proportional to the angular momentum of the rotation. And then you have the nuclear moment of the hydrogen, and they couple together. That's this term here. And then you also have the external magnetic field, which would also like to couple, or also couples to these spins. And so there's a competition between should they rotate independently in an external magnetic field, or should they be coupled together. And we're in the intermediate regime, so it's neither Paschen-Bach nor Seemann. And that means that all these states are spread out in non-uniform ways, not like in the Seemann regime where it's all linear, for example. And now if you look at these G factors here, they're really small, because it's basically two things that are on the order of a nuclear magnetic moment coupling together. So it's kilohertz per millitesla. So in a way, these transitions are relatively insensitive to magnetic field, but you still get this spread here. And what's decisive is that depending on J, you always have a transition. For example, here it's this 10 kilohertz transition between the m equals -3 halves and the -1/2 minus. That's what we call this guy here. That's 10 kilohertz, and if I compare that to J equals 2, that would be 14 kilohertz. And it keeps going up. So this particular transition here, this one and this one, it always stands out and it has different frequencies for different J levels, which means it's a signature transition. Whenever we can make a transition with this frequency, for example, we know we are in this manifold and we must be either in that state or this state. And the fact that we can make the transition or not make the transition will tell us what the final state was of this and which state we are in. So again, we use Raman transitions. It's a really weird type of Raman transition, in fact, because the energy difference here is extremely small. What I'm showing here is a so-called carrier transition. So in this case, the energy difference just corresponds to the difference between the energy levels, which for these really small ones would be between 10 and 40 kilohertz, for J between 1 and 6. So it's a small energy difference. However, making such a transition wouldn't tell us anything, because we have no sign of that transition happening that we could pick up with our logic line. So we have to do a sideband transition. And the sideband energy difference is on the order of 5 megahertz. That's just the normal mode frequency in this trap, the stretch mode or near stretch mode. So that's about 5 megahertz. So it's a lot more than the internal energy. Things are kind of turned around to what we are used from Raman transitions, where the internal state typically is many megahertz or something like that. It really depends on the system you're talking about. And then your sideband is just a little bit spaced out. Here it's the other way around. You have a very small energy difference between the internal states and a much larger between the motional states. But it doesn't matter. The Raman transition still works just fine. So if we do such a transition like this, we will actually leave a trace in the motion of this 2-ion crystal that we can observe. And also, since we move between different M levels and we in the end know which ones we are in, we can align the angular momentum to a certain axis. We don't not only control J in this way or know J in the end, we also know the orientation of the angular momentum relative to the quantization axis. The way this is done is we use a CW laser at 1051 nanometers, very far away from the electronic transition, and split it into 2 beams. One goes through this AO, which is at frequency nu, and then this AO is at nu plus the sideband frequency, plus the little energy difference between these 2 states. We shine that in. One is pi and one is sigma. That gives us the selection rules here, that we go up pi and then go down sigma, for example. And when we can make this transition and pick it up with the ion, something magic happens, if you wish. We can project into a pure state. So that's the part that I think Schrödinger would not have liked very much. But anyway, we can do it in the lab every day. So the trick here is, when you make this transition, before you have seen the result, you could be in any of these states. So you have a density matrix with lots of entries. But if this transition really works, you're going in the external motion from the ground state to the first excited state. And now if I look on my calcium ion, whether I'm in 0 or 1 of the motion by doing the red sideband, I have projected into this state, and I'm in a pure state of the molecule, a pure quantum state of the molecule. And that basically means, since I'm also doing this in a sense non-destructively, I can repeat this in a sense. I can do the same transition the other way around and try to do a pi pulse and do that on the sideband, and I can actually confirm my result. So I can do this several times just to make sure that I'm really projected into the right state. And that allows to be in a pretty pure state. All this stuff takes time though, and we start in a very large distribution of states. So we are actually using a trick that speeds up getting into the states that we are more interested in. We cannot always do the detection and look on the logic ion. And this trick is very simple. You just have to couple to the environment and add entropy. So again, you still drive this blue sideband, but the next step you do now is, rather than detecting, you just cool the motion. So you use the sympathetic cooling ion to cool the motion. And that means you're taking away this information, and am I in 1 or 0, you put it into the environment. And it makes this transition irreversible. If I now shine in the same red sideband, I can't go back here because I've lost that energy from the cooling. And we can do this on all these states here. So by doing these 2 steps, doing a transition, then cool and make it irreversible, we can basically push this in a one-way street towards the states we're interested in. For example, this state here, because that corresponds to one of the states that are connected by the signature transitions. So in this way, we can push more population into the states we're interested in by using the cooling as an entropy removal tool. And then finally, we can do these transitions, and the result you can see here. This is the Raman frequency difference, and as you can see, it's a very small difference. It's just a few kilohertz in the for these smallest lines here. And if we are not doing the optical pumping, if you wish, with the cooling on the logic ion, then we basically see no signal here. But by concentrating the population in our signature levels, we can make these visible. So now we have something to grab onto. We can actually see there's something happening, and these are the transitions. And even better, we can go into pure states by doing these measurements. And once we have signified and certified that we're in such a pure state, we should be able to do coherent interactions with this system. Basically, we can use the signature transition almost like it is a qubit. And so doing that, we can also use the carrier now. With the sidebands, we can basically find whether we are in a certain state, because we can make that transition from that state. So if we leave that state, the sideband won't work again. And that's what you can see here. I can now do a carrier transition, for example, from j equals 1 to j equals 2. Sorry, you can do no, that was totally wrong. I can do a carrier transition in j equals 1 or j equals 2. So these are 2 different experiments, 2 different cases. And if I can make this transition, I will not find the molecule in this state anymore. So basically the probability of finding the molecule in the state I think I am will go down when the transition happens, and then go up again. And this is j equals 1. This here is j equals 2. So we can do this in different states. The only change that has happened here is that when we initially heralded the transition, it was in j equals 1 here and in j equals 2 here. And then we can start the experiment. We have to do this many times for each of the points. So all these points come in more or less at random, because all the time while we do this experiment, the blackbody radiation in our experiment is scrambling the rotational states again. But that scrambling is slow compared to our spectroscopy. So we can do a few experiments before the rotational state gets spoiled. And so in this way we can get these high contrast lines for j equals 1 and j equals 2, for example. We can further certify that this is really sort of a qubit by doing Rabi frequencies, Rabi flopping. Note that this is not 0 time here, so that's why it doesn't start at 1, but you can see that the contrast is maybe not great, but this is a molecule, so it's not a qubit that we have worked on for years to make it as good as possible, and we're trying to get it better. But we can see pretty good Rabi flops in j equals 1 and also in j equals 2. The times are different, and they correspond to the dipole matrix elements, or not really dipole, it's Raman transitions, the Raman Rabi frequencies that you can calculate. So everything looks pretty good. You can also do Ramsey experiments just to see how far can I drive this, what's the coherence. And here we are helped a little bit by the fact that the magnetic moments in this molecule that we're using are relatively small. So it's not very much affected by magnetic field fluctuations, for example. And here you see a Ramsey fringe where the delay is about 15 milliseconds, so that would correspond to a resolution of about 66 Hertz. And as you can see, the contrast is still okay. It's not perfect, but it's looks okay. J equals 1 and J equals 2 work. So looks pretty good. We can do more, and this is where actually another tool comes in. We can use frequency combs rather than a CW laser. And what that allows us is to do transitions between different J levels. So rather than a few kilohertz, these are now terahertz apart. And that's a frequency difference that you could bridge with two CW lasers that are detuned by a few terahertz. But for each J transition, you would need to tune that laser by a few terahertz, one of them. And so that's not very efficient. What you can do with frequency combs is that you can think of them as actually a laser that has a lot of lines at the same time. And even better, if you think about a certain frequency difference, and it's actually, it comes out in the comb teeth here, so for example like this, then the next pair over has the same difference, and the next pair over has the same difference, and so on. So in a way, for a Raman transition, these two and these two work on the same transition, and so will these two. This is a trick that Chris Monroe and company use all the time for their 16 gigahertz hyperfine transition. So this was already shown in atoms before we use it for molecules, but it's not limited to 16 gigahertz. As long as the spectrum of the comb is much broader than the transition frequency you're trying to bridge, this trick will work. Almost all of these comb teeth will have partners that work with one of these photons here to drive this transition. And the only thing you have to worry about is that they work in phase. So you have to compensate the dispersion of that pulse. That's basically what it boils down to. But once you do that, you can make almost the whole frequency comb work for you to drive the transition. So the way we do this in the experiment is we use a jerk mirror here to basically pre-disperse the pulse. We give it a negative dispersion because after that we go through quite some glass, the acousto-optic modulators, and then the windows of the trap chamber and so on. So we have to pre-compensate for that, such that when the pulses arrive on the molecule, they have very low dispersion. And the other thing you have to make sure, of course, is that the pulses collide on the molecule. So we have a variable delay line here that allows us to get the pulses overlapped on the molecule. And in effect, what we do is really have the path of this beam and this beam have the same length. And if that happens, you can really do Raman transitions that can also be quite a bit larger than just a few comb teeth in spacing. And then these two AOs, they allow us to bridge the free spectral range, which is about 80 megahertz in our experiment. So we can change the difference between these two AO frequencies in such a way that we can essentially shift the upper comb relative to the lower comb in such a way that we can hit any difference frequency that we want between roughly 0 and 5 terahertz or something like that. So doing that, we use the CW laser, as I showed you before, to do state preparation. Then we can use one of these comb pulses and drive the carrier, which means we leave a certain rotational manifold, for example J equals 2, a certain state in there, of course, that we've prepared. And then we should also see that we arrive in another state. The Raman selection rules for a linear molecule allow only delta J equals 2 transitions, so we arrive in J equals 4 in this case. And indeed, we can see when we deplete the J equals 2 population, we find it in J equals 4. So we can, in this way, we can really verify we are going to the state we think we're going to. And the frequency, the width of these transitions is basically limited by the comb coherence at this point, and it can be fairly narrow. When you look at the offset here, this is minus 1 kilohertz, this is plus 1 kilohertz, and we can find these line centers with very small uncertainty on the order of 20 hertz or so. We can also do Rabi flopping, so even between different J levels you can have good qubits if you wish. So now these are at a few terahertz, not at a few kilohertz. They are we think the coherence here is limited by the comb coherence. So how well can we discipline our frequency top, basically. With doing these delta J equals 2 transitions, we can measure different frequencies here. So this is the collection of what we've done so far. And we get a lot of digits here. We don't need to count them. The relative uncertainty of the one we can determine best is about 2 times 10 to the minus 11. So that's pretty good, which means we can now compare the energy difference between these different states and find rotational constants. And in principle you could go on here, but you only have a certain number of transitions and it gives you a certain number of rotational constants. We can calculate those by first subtracting the effects of the magnetic field. Then we have to think about the spin-rotation coupling that gives you a split of the centroid. You find the centroid and then finally you get the rotational constant. This is what our theory friends, Philip Blesso, finds in theory, and we see this in the experiment. So we have pretty good agreement, but the theory is not quite as accurate as the experiment, which means with this experiment we can basically give the theorists benchmarks to test their calculations on that will last for quite a while before they can reach this accuracy, I would guess. So I think that's pretty much it. Oh, well, one more thing. One really simple trick we can do is, that we all know from atoms, now we can do it with molecules, is we can actually entangle the calcium atom and the calcium hydride molecule, qubit. So this is a rotational qubit if you wish. The trick is very simple. You do a pi-Hertz pulse on the calcium hydride with the CW laser in this case, so it's in the same manifold in the J equals 2, and you get this state here, but you do it on the side band. So in this part of the state you're in n equals 0, and here you're in n equals 1, and then all you have to do, it's really simple, is you do a red sideband pi pulse on the calcium, which now entangles the calcium S and D state with the molecule. We can do our usual parity measurements here that tell us that the electronic state of the atom is entangled with the rotation with a fidelity of about 0.87. So you can think of this as the S state of the atom corresponding to the molecule rotating in a certain orientation, and the D state corresponding to the molecule rotating in a slightly different orientation. That's the idea. And the point of this is that we can basically use the rotation of a molecule as a qubit if we wanted to. I'm not really sure what it would be good for, but in any case we can do it, so we did it. And that's pretty much all I have to tell you. I think you can read the summary because I'm out of time, I would guess. Yeah. So the most important thing I have to do, of course, is to thank everyone in the ion storage group for providing such a fruitful environment, and I already pointed out the particular people that make this experiment possible. And I thank you for your attention.
Yes, nice talk, really. I was wondering how many transitions finally you know, or how many energy levels do you know finally in calcium H class? What I mean is that suppose that I'm a molecular spectroscopist and I want to know all the potential because to test the theory and so on.
Right.
And so how much time will it take to get all the transitions from all the potential world compared to, I would say, traditional molecular spectroscopy stuff and so on?
Yeah. So getting one of these lines that I showed you takes about 20 minutes, but we get them in parallel because at least right now our state preparation is more or less random. So we just find the state. And so the experiment that we're doing finds the lines in J equals 0 to 2, 1 to 3, and so on, up to 6, all in parallel, and it takes about an hour or so. So that's not so bad. I think what you would like to see is vibrational transitions as well. And that would take a different approach. So a single frequency comb is not broad enough, or at least unless you do something special, it's not broad enough to do that. You would need two combs that are really separate, and you have to phase plot that. This can all be done in principle. We are not doing it yet. The times would be similar, because once you find the pure state of the molecule, you can do a transition to wherever you want, and then you will see it. So I think it's not a crazy long time, but it's also not milliseconds. But in principle, you can also look at the vibrational transitions. If you ask about excited electronic states, that gets very hard with a single particle, because then you're lost in Hilbert space again. And so I can probably figure out what the ground state potential is, or at least the states they're in. It's a different question that I can't answer, is how do you take this information and actually make like a potential energy surface out of it. One good news that I didn't emphasize enough maybe is that all these techniques are very general, so I can also use this on polyatomic molecules. So in principle there's a lot of potential there. How well it will work, we will see.
Then theorists are not always at ease with if the system is too complicated, so it's okay for the diatomic point.
Well, that's fine. Yeah.
So,
Yeah. Okay. No, you were basically at the same time. Yeah.
so you had a 10 to the minus 12 precision? Or
11. That's 10 to the minus 11.
That's close to the best molecular spectroscopy out there, right? Maybe an order of magnitude away?
I'm not really sure,
Okay.
because it's very hard to keep track.
Yeah.
But I think it's not too bad.
And on a single molecule.
Yeah, and another thing that I didn't mention is that people have ideas how you can use diatomic symmetric molecules for tests of alpha dot, and you might mention that. So there's actually potential for precision spectroscopy. This is not just because we can do it. There might be physics questions that we can answer.
Beautiful. How much are you dependent on the stability of your motional frequencies?
So let's go back a few. So basically we are dependent on that to do the side plans, which tell us we're in a certain state. But then when we do something like this, we do carrier transitions. Because all we need to know is that we leave a state and we arrive in another one. And that's where the side plans come in. So the motional stability does not play into this, other than you have maybe second order Doppler shifts or things like that, which may be weird to talk about with molecules, but at the precision we're getting at, this is actually not something you have to can forget about. What we are more worried about is things like how stable is the magnetic field and how stable is the micromotion. For similar reasons. When you have micromotion, you're basically moving in electric fields, and that affects molecules. They couple by their dipole moment to the electric field. So we're more worried about that than the motional stability. I don't know. Maybe we're out of time.
No, I was just curious about when you have those ions created in the trap.
Yes.
I suspect that they come from the collision from residual H2 or something, right?
Yeah.
So my point is that do you wait for some time for the ion to relax the internal motion? Because in principle it can be created in any state, right?
Yes.
So I was wondering how much time typically did you have an estimate on that?
Yeah.
For the relaxation?
So yeah.
Did you try to?
So calcium is really nice because it doesn't react very much with hydrogen, which means we have to put an extra hydrogen into our cell. So we trap 2 calcium ions, then we put hydrogen gas in, quite a bit of partial pressure actually, 10 to the minus 6 torr or so, and then it reacts. Then we have to pump out the hydrogen, and that takes on the order of 5 minutes or so just to reach a good basic pressure where you don't have constant collisions with the remaining hydrogen. So I think you could wait a lot less. The relaxation to the vibrational and electronic state, ground state, is probably a second or so. I mean, that's a very generous number. But in practice, we have to wait a bit longer than that. And that helps us. In the long run, we would like to do this cryogenically and also do it on on symmetric molecules and so on. And so then we can't rely on the thermalization anymore. We have to play other tricks, like create them in a certain state, or search a very large number of states, or we are also thinking about using buffer gas collisions to relax them to 4 Kelvin or something like that. If you use helium as a buffer gas close to 4 Kelvin. So anyway, yeah, there are lots of things I never
All right,
talked
let's
about.
thank our speaker again. And I think if there's other questions.